Now, before we derive the transfer functions of some mechanical system, electrical system, and electromechanical system. First, let us first model the system in terms of a differential equation or in time domain. So for a translational mechanical system, so our mechanical system will be divided into two parts. We'll have the translational, and the other one will be the rotational mechanical. And after that, we go to electrical. Then we combine them. We go to electromechanical systems. For a translational mechanical system, the very basic example of translational mechanical system is the mass spring damper system, damper systems. So example of this are the shock absorptions of cars, anything that has mass and spring and friction uh, can be considered as mass spring damping system or damper system. So let us look at the different components of this kind of system. First, we look at the spring. Look at the spring. So what is a spring? A spring is in mechanical system. This is actually a stiffness element. It can store energy by pushing or by pulling the spring. But in electrical or in control system, control engineering, when we model the spring, we use the ideal version of the spring to simplify our analysis. We do the ideal version of a spring, because the non-ideal version of a spring, we know the Hooke's law that if you have the force, apply a force, and the displacement of the spring, it will be proportional to that. But at certain point, if you apply larger force, then what happens is the it can go into that direction or it can go into that direction. It will not be linear relationship between the force and the displacement. So here in translational, we in control energy or control engineering, we assume that we are in this region, the working region of the spring, or simply the ideal version of the spring. When we say ideal, the spring is massless spring, and also it has no damperless. So if we apply a force, so if this is our spring, so if apply a force at that direction, and we have here what we call K. K here is not the static gain. This K here is the, let's just make it KF. So this is the, or KS. Let's just call it KS, spring constant. KS here is the spring constant. This is the proportional constant between F and K. Or this is the, if you look at the graph, this is the slope of this one. So if we solve for F is just equal to, it's proportional to X. But if we include that Ks, spring constant, then the force is just equal to, due to friction or due to spring, let's call it Fs. And let's just make it in time domain, small f. F of S will be equal to Ks of S times the displacement x of t. This will be the model for the spring if we are looking at F as our input and the displacement as our output. So this is a force is the input and output is the displacement. Force displacement. But sometimes we don't want the displacement. We want the velocity of the motion. So in that case, the model will become, instead of k x of t, it will become, because x in physics, we know if we want to determine the velocity of a certain body or motion of a certain body, this is just equal to the change in the displacement with respect to time. Or in other words, this is just equal to dx dt. If x is in a function of time. So if you want to determine the force in terms of velocity, because you want our output to be the velocity, then this is just be equal to, so if we solve for x from here, dx will be equal to v dt. So x of t now will be equal to the integral of v dt, where v is the velocity. So here we have k of s times the integral of v dt. And this will be the model if this is for a force velocity system. So if you want your velocity to be your output, then use this one. And if also the other one is if you want the acceleration, the relationship between these two, acceleration will be just equal to the second order or the first derivative of the velocity. It's the change of velocity with respect to time. So you just change that velocity with respect to time, then you have the acceleration. So this is spring for ideal spring. So this is how we model the spring. Next, the other one is the damper. A damper, this is the a element due to the friction between bodies that are moving. So the higher the friction, the higher the force that you need. So the symbol for this is this symbol. So if you can see this is the symbol for damping or damper. And we can have a constant damping coefficient kd. And if you apply force, now this force f of t, then here we have I didn't write the output, so the displacement is in that direction. And also this one, we have the displacement also here if you want your displacement as your output. So if for damper, the damping depends on the velocity. It depends on the velocity. So if we derive the formula now due to damping, let's just call it FD. Or some other references, they name it viscous damping, viscous damper, so on. It's just equal to, again, it's proportional to the velocity. So we have a damper constant or damping coefficient. We can just name this one K D for the damping coefficient or damping constant. So if you multiply this with the velocity, so velocity, that is x dot t. So this means it's the first derivative of x with respect to time. Because velocity is the derivative of x with respect to time. So I can just write it using the dot notation. Now, what if we have more than one spring and more than one damper? So if a spring, you have two springs connected in series. So here we have two springs. This is KS1 and we have KS2. And if we have a force here, then this is equivalent. This is in series spring. This is equivalent to, it's the same formula. If you remember in electrical circuits, this is the same formula as the formula of a parallel resistor. So if you want to determine the equivalent of these two, we can just make it one spring. The equivalent will be equal to, this is f of t. This one will be the parallel formula for a resistor or resistance. Ks1 times Ks2 all over Ks1 plus Ks2. So you just do the formula for the parallel resistors. So what if they are not in series but in parallel? So if they are in parallel, for spring, then so we have two springs, or even more than one, more than two springs. And we have here f of t. Then if this is ks1 and ks2, so the equivalent of this single spring equivalent is just equal to the opposite of parallel of it's the series. So we just add them. This is just ks1 plus ks2. So this is for the spring. For a dumper, it's also the same. So if this is in series, then the dumping constant equivalent will be this formula kd1 over times kd2 over kd1 plus kd2. If it's in parallel, then you just add them. So the same concept. So this is spring and damper. So the last one is for the mast. The mast is just a mast. So if we have a mast, a body with a mass m, then if we apply force on the body, so if this is our reference, we have a reference somewhere here. Then there will be a displacement into that direction. So if this is f of the t, then this is x of t. Then there's an opposing force due to that mass, and we can call that f of m. And that is just equal to, according to Newton's law, that's just equal to the product of the mass and its the body's acceleration. And if you want to your output to be the displacement, so this one now, the force due to the mass will be mass times x, the displacement, then the second derivative of the displacement, because acceleration is the change, or a is equal to v dot, and v is equal to x dot. So if you take a is just equal to the second derivative of x. So here we can also write it in terms of the velocity, m times the velocity v dot. So these are different model for mass, and it depends on what is your output and what is your input. Our input are here are all forces, but the output are different. Here, if your output is the acceleration, here for displacement, and this is for the velocity. So these are the three different components of a simple mass spring damper system. So if we take an example of a mass spring damping system, so if we have here, let's say, so if we have a mass m, then we have a spring here, and we also have damping. So let's just do the symbol. We have a damper. Then if we apply a force F into that direction, F of t, then there will be a displacement also in that direction, x. So if this is K due to spring 1 and the damping constant, or just Ks and Kd. Determine the transfer function of this system. So here, our output is x. This is our output. And this is our input. So for that, we should take our derivation of the different forces due to, so displacement, we'll use this one. We will also use this one. And for the mass, we will use the double dot notation. And applying second law of Newton by taking all the sum of the forces, the free body diagram, draw the free body diagram. This is M. We have force here. We have force due. This is F of t. This is force due to the friction, or the spring, Fs, and force due to the damper. So if you take the summation of all forces, this should be equal to the mass times the acceleration. And net force, we have, we to the right is positive. So we can have f of t, the input. Then f of s is going to the left, so this is minus. Then these are all in time domain. These are all in time domain. F of s minus f of d in time domain. And this should be equal to mass times the acceleration. But we don't want acceleration because we want our output to be the displacement. So we replace it with the double dot x of t. Then force is input, so this is our input, so that's it. Then for the force due to the spring, we already know that that's just equal to k, the constant, multiplied by the displacement, x of t. Then for the damping, this is equal to the damping constant, kd. You multiply it with the velocity, but we want the displacement, so this is uh here displacement is the x dot d, x dot t, the first derivative of the displacement, and this is equal to m times x double dot t of t. So this is now our differential equation. So if we derive the Laplace of this one, then we can also derive our transfer function. So f of t, this will become f of s minus k, this is just constant, then this will become capital X in S domain. Then we have a first derivative, so kd, first derivative, s raised to 1, so multiply it by s. And again, we assume here there's no initial condition. No initial condition. Initial condition. So that this will be kd times s times the displacement in S domain. Then this is equal to the mass multiplied by the second derivative. The Laplace of the second derivative will be s squared times x. And remember, x is our output, input is f of s. So we can rearrange this now. F of s is equal to, we can factor out that x of s. So we have m times s squared, and this will become positive ks plus ks. Then we have, or this k plus k, then plus also, this is s. kd times s, kd times s. Then output over input, our output is x. So x of s now all over f of s, the transfer function will be equal to 1 all over ms squared plus kd times s plus ks. And so that we can determine the different parameters, the damping ratio, the static gain, and the natural frequency. We need to rearrange again this into the standard form. So you multiply it with 1 over m, 1 over m. So the transfer function now in standard form will be 1 over m all over s squared plus kd all over m times s plus k times s all over m. So from this, we can determine the different parameters. What is the natural frequency? Omega n. So omega n, so remember the format of the standard transfer function. So it's k omega n squared all over s squared plus 2 zeta omega n times s plus omega n squared. So this is the standard form. So from that, we can determine our omega n. First, omega n squared is equal to, so we can solve for omega n squared. This is just equal to the spring constant all over the mass. Or omega n is the square root of the spring constant over m, or the mass. Then for the, so this is the natural frequency. For the static gain, k omega n squared, this should be equal to k omega n squared is equal to 1 over m. So solving for the static gain, this will be equal to 1 over m times omega n squared. 1 over m times omega n squared, but omega n squared is equal to k as all over m. So therefore, the static gain now, you can cancel out that k or m. K now will be equal to 1 all over k's of s. Then lastly, for the damping ratio, zeta. So 2 zeta omega n, this should be equal to kd all over m. Then solving for zeta, zeta will be equal to kd all over 2 omega n times m. But omega n is equal to the square root of this. So zeta will be kd all over 2 the square root of k over m times m. Then we put m inside the square root, it will become m squared. You divide it by m, it will become m times k. So therefore, this is ks, spring constant. This is the spring constant. So the damping ratio now will be equal to kd all over 2 the square root of ks times the mass m. So from the transfer function, we derive the different parameters of the mass spring damping system. So this is how we do, this is an example of a translational mechanical system.